In my last video, we identified a problem with generative AI and large language models. We discussed that they lack a structural understanding of the physical reality. We talked about how treating text predictors as decision-making engines for the physical world is highly problematic. So today, let's shift our focus from models that just describe the world to models that simulate it. I am Scott Pesanowski. I specialize in geospatial data science and artificial intelligence. Specifically, I build AI systems for continental scale disease prediction and simulation, and I advise major banks and environmental organizations on AI implementation. These applied applications enable domain experts to use the tools to improve global health or banking performance. In doing this work, I have seen firsthand that predicting real-world outcomes requires much more than just processing language or generating text. The physical world is dynamic, high-dimensional, and governed by strict laws of physics. Today, we are exploring geospatial world models. These are the next step to overcome the limitations of text-based models. But I want to be clear up front. While we discuss the potential these architectures hold, current models are still in their infancy, but the direction is set. We are going to explore systems designed to not just look like the Earth, but to think like the Earth physically. Let's first define what a world model is not. Right now, most of the artificial intelligence you interact with is either generative or supervised learning models. Whether it is a large language model, writing an email, or an image generator creating a landscape image, these systems are fundamentally probabilistic. The language models look at large amounts of training data, text, and predict the most statistically likely next piece of information, whether that is the next word in a sentence or the next pixel in an image. Similarly, you have long-standing models like recommender systems on your favorite platforms, such as YouTube, Netflix, and Amazon, or even the notifications you receive from your credit card company when a fraudulent charge occurs. The supervised machine learning models learn from past views or transactions and then sift through large amounts of data looking for patterns or anomalies that fall outside those patterns, such as fraudulent transactions. A world model is fundamentally different. It is an artificial intelligence designed to learn the statistical structure of space, time, and physical constraints. It does not memorize patterns. It builds an internal predictive simulation of physical reality itself. It learns how light falls on a surface, how terrain slopes, and how objects respond to force. And it does this along with competing or complementing physical processes. As this technology becomes more widely discussed, there is a common misunderstanding in the industry that we should address. It is the divide between renderers and simulators, or simply put, Hollywood physics versus reality. Right now, tech companies are showing off AI that can generate realistic video environments from a simple text prompt. If you ask one of these visual models to generate a video of a flash flood hitting a city block, it will produce a highly detailed, visually accurate clip in which the water appears to flow correctly. But looking real is not the same as being real. That visual renderer is operating on Hollywood physics. It is generating computer graphics. It is not calculating actual hydraulic pressure, terrain roughness, mass conservation, or gravity. If you are an urban planner trying to reinforce a critical railway, or a public health official deploying emergency resources, a pretty 3D animation can be very misleading. When human lives and critical infrastructure are on the line, you do not need a cinematic approximation. You need a deterministic calculation. You need a model that respects Newton's laws and maintains a geometrically faithful representation of reality. This is the true definition of a physics-informed world model. However, we must be realistic about where this technology currently stands. Right now, these models require immense computing power, and integrating multimodal datasets, like combining real-time weather, structural physics, and human mobility, is highly complex. We are not yet at a point where a city manager can buy an off-the-shelf world model to perfectly simulate their entire municipality. Current iterations are specialized and often isolated to specific research applications. Yet, the foundational architecture is being built today, and the shift from describing the world to simulating it is underway. To understand how these systems operate, let's examine how we construct a world model from raw data. Creating a world model is fundamentally different from training a standard chatbot. It is a rigorous engineering process that moves from gathering physical data to enforcing the laws of nature. Building a world model starts with the data, and you do not just feed it text from the internet. It ingests large volumes of multimodal physical data. This includes high-resolution satellite imagery, continuous weather sensor feeds, topographic maps, and human mobility tracking. Fusing these distinct data streams creates a continuous, overlapping historical record of how specific environments change over time. Once we have that data, we need a mathematical structure to process it. The industry relies on advanced architectures such as visual transformers and spatiotemporal graph neural networks. More simply, these are specialized AI structures designed to understand not just what an object is, but exactly where it is in space and how it changes over time. They map out the complex web of relationships in an ecosystem or a city, tracking how a single change in one location ripples through to the rest of the physical network. When we talk about processing this data for world models, you will frequently hear the acronym JEPA. This stands for Joint Embedding Predictive Architecture. In simple terms, a JEPA model learns abstract representations of a situation rather than trying to recreate each raw pixel. For example, if a generative AI model watches a robot pick up a mug from a cluttered table, it might waste computing power modeling every pixel of the table's color or background pattern. A JEPA model ignores those irrelevant details. It focuses only on what matters, such as object positions or spatial relationships, and predicts what could happen next. By predicting abstract representations instead of raw pixels, it becomes a highly efficient engine for physical reasoning and understanding the world. The model training process differs even more. Traditional AI is often trained showing it millions of labeled pictures, so it learns to identify patterns. World models, however, use a method called self-supervised learning, focused on the next frame prediction. They feed the model a sequence of past physical events, such as the progression of a storm or the buildup of traffic, and ask it to predict the exact physical state at the very next moment. Most importantly, they apply physics-informed constraints during this training. If the model predicts a scenario that violates the laws of fluid dynamics, thermodynamics, or gravity, the system penalizes it mathematically. The AI learns the rules of reality through trial and error, forced to operate strictly within the boundaries of physics. Finally, they must prove that simulation is accurate before it is used to make decisions. They do this through rigorous validation. They take a known historical event, input the conditions leading up to it, and see if the model's simulation matches the actual real-world outcome. When validating these architectures, they ensure that any calculated environmental variance is strictly bounded within the scope of the specific architectural evaluation. This proves that the model is calculating true physical dynamics rather than just making a statistical lucky guess. Once you have a validated physics engine like this, it changes how to approach spatial modeling entirely. It takes us far beyond the traditional concept of a static digital twin. For some of the tech people, you might be listening to this and thinking, we already have this technology. For years, the geospatial and architectural industries have talked about digital twins. A digital twin is essentially a highly detailed digital replica of a physical asset, like a bridge, a building, or even a whole city. However, standard digital twins are often just static 3D maps, or sometimes fed real-time data. They are very useful for visualizing what currently exists, but they struggle to predict complex, interconnected future events. They are very rigid. A world model takes this concept of a digital twin and turns it into a dynamic active engine. It can scale complexity because it can model so many processes based on the world dynamics it learns. Let me explain this by using some of my own work as an analogy. When we build AI-based systems for continental scale disease prediction, we deal with chaotic environments. A disease outbreak does not happen in a vacuum. For example, in some of our past disease modeling, elevation proved to be a critical factor in predicting disease spread. Elevation is most commonly used as a beautiful hill-shade backdrop on a map, or even visual grounding in game engines. But when we feed that data into an AI architecture, it transforms from that pretty picture into a highly valuable real-world analytical layer. Because elevation and slope directly influence soils, vegetation, wildlife, and complex human infrastructure, our models use the stable terrain geometry to compute precise environmental risks. The AI is not just rendering the shape of the land, it is calculating exactly how those physical forces interact to create a breeding ground for disease. Understanding those physical interactions is a significant step forward from static maps, but if we stop there, we are still only forecasting what might happen. When you introduce a true world model into this scenario, you enable domain experts to go beyond prediction and simulate the future. Because the model understands the environment's physical rules, a public health director or a city planner can test complex interventions in a safe, simulated space before they ever spend $1 of their municipal budget. Imagine a city planner wanting to reduce the urban heat island effect, which directly impacts everything from energy grid stability to the breeding grounds of disease-carrying mosquitoes. With a true world model, they would not just guess where to plant trees. They would input a localized wind corridor and strategic shading into the simulation. The world model then calculates the physical changes in solar radiation, the shift in wind flow, and the resulting drop in street level temperature. The domain expert can instantly see how that physical change ripples out to the effect of public health outcomes. We are moving from systems that simply tell us what the world looks like to systems that allow us to test how the world works. But to run simulations that complex and accurate, the physics engine needs to be fed the right information. It needs to perceive the Earth's current state with high precision. And that brings us to how we actually ground these simulations in reality. For the geospatial industry, I'd like to make an important distinction here. That's the difference between a foundational model and a world model. In my work so far, I don't develop foundational models or world models from scratch. Instead, I build custom AI-driven prediction architectures for global health applications. When I build these pipelines, I view foundational models as the ultimate sensory systems. Consider the NASA and IBM Prithvi Earth Observation Foundation models as practical examples. The Prithvi family includes specialized architectures, with one model focused on terrestrial land Earth observation, and another on atmospheric data. Because foundational models are inherently versatile, we do not have to limit them strictly to a single use case. In practice, we can deploy models like Prithvi across multiple downstream tasks, including land cover classification, vegetation monitoring, and urban footprint mapping. Prithvi efficiently processes raw satellite data to establish a factual baseline of the environment. This provides a clear, accurate picture of the current physical state on the ground. But perception is only step one. A true world model is the physics engine itself. It takes the ground truth established by a model like Prithvi and simulates what happens next by applying the laws of physics and cause and effect. Let us look at a real-world application of this in action. Google Research and the European Center for Medium-Range Weather Forecasts recently built Neural GCM. Neural GCM is a true geospatial world model for the Earth's atmosphere. Instead of just looking at past weather maps to predict the next one, Neural GCM codes the underlying fluid dynamics and thermodynamics directly into the neural network. It successfully simulated atmospheric conditions and outperformed the world's leading traditional weather models. Understanding the physical constraints reduced forecasting errors by 40% and enabled accurate prediction of extreme weather events. We also see this heavily applied in the autonomous vehicle industry with NVIDIA's Cosmos world models. Instead of risking lives by driving millions of miles to test rare conditions, these companies use Cosmos to simulate complex urban physics. The AI computes friction, object permanence, and physical collisions. This allows fleets to safely rehearse and adapt the physical world before the rubber ever meets the road. As we adapt these powerful physics engines, a major strategic question arises regarding control. If you are managing critical infrastructure, national defense assets, or sensitive public health data, you cannot rely on an opaque, external third party to tell you your city is safe. This entire simulation pipeline cannot exist as a black box public cloud tool. It should be entirely sovereign. And sovereignty simply means your data stays behind your own firewall, under your complete control, and never leaves your secure digital walls to train a public cloud model. In my work with institutions and global health organizations, this level of security is non-negotiable. Instead of standard publicly deployed models, I strongly advocate for secure, sovereign edge computing infrastructure. By deploying open-weight models locally and fine-tuning them within your secure boundary, your institution maintains total ownership over its physical intelligence. Cities and nations must maintain absolute control over their sensitive data, localized geography, and predictive systems. You need a custom, sovereign solution that your local institutions control, understand, and trust. Today, we covered exactly why generative AI struggles with physical reality and how physics-informed world models will reshape geospatial analysis. By applying advanced geospatial models to physical systems, we are turning chaotic information into an active diagnostic tool that proactively protects communities. We are moving from reacting to the noise to governing proactively. However, deploying this technology requires a deep understanding of foundational models, hyper-local geospatial data, and a strict requirement for transparent, sovereign edge computing solutions that your institutions actually control. If you are an institutional leader, agency head, or a domain expert looking to build secure, custom prediction architectures, you do not have to navigate this transition alone. I regularly collaborate with organizations to translate complex geospatial data into production-grade sovereign AI pipelines tailored to high-stakes operational environments. Whether you need to simulate regional public health vectors, manage critical infrastructure, or design secure spatial architectures, let's connect. Reach out to me directly through the contact links on my website in the description below. Let's discuss how we can build custom, physics-grounded intelligence for your specific institutional needs. Thanks for watching.